Hi, this is a spotlight video for NIPS 2017 paper. My name is Feng Nan. As machine learning models get more and more complex, we're able to achieve higher prediction accuracy at the expense of higher prediction costs. Some of such prediction costs include feature acquisition cost, where extraction of each feature incurs a cost, communication computation, latency cost, memory and battery constraints, etc. Here's an example of a feature acquisition cost in a medical diagnosis system. Each patient has at least features corresponding to medical test results. Each medical test carries certain costs in terms of money and risk. So good prediction models require only a small number of tests per patient. An example for communication latency cost is the mobile application. Suppose we want to run an image prediction task on the phone. The prediction model is so big and complex that it can only be deployed on the cloud. So given a test image, the phone must first upload it to the cloud and run the complex model there and finally get the prediction output back. This is costly in terms of communication and latency. So what are the solutions? We can try to speed up the complex models by investing in faster computers, but this is quite expensive and doesn't reduce the communication latency cost in mobile computing. Or we can just use a simpler model such as a small neural network. Such models are so small that they can be deployed onto a mobile device. It indeed lowers the prediction cost, but often suffers in prediction accuracy. The question is, can we lower prediction cost without losing accuracy? We propose adaptive approximation as a unified framework to address such resource-constrained ML problems. Given a high prediction cost model HPC, we learn a simple gating function G as well as a low prediction cost model LPC, such that the G distinguishes the easy versus hard examples and predicts the easy ones using the low-cost model and sends only the hard ones to the complex model. In mobile applications, G and LPC can be deployed locally on the phone so that the easy examples can be predicted on the device itself. This way, we can maintain the overall prediction accuracy while reducing the average prediction cost over the examples. Here's a toy 2D example. There are two classes, red and blue. We learn a complex model using kernel SVM that gives a good decision boundary, but prediction cost is high due to the many support vectors. Using adaptive approximation framework, we learn a linear gating function that divides the input space to easy versus hard. On the easy region, a linear predictor suffices, whereas the example in the hard region, colored beige, is still predicted using the SVM. You can also use gradient boosted trees as simple gating and prediction models. Here, only a very small fraction of examples are sent to the complex model. Looking at the cost accuracy curve, we see that this approach maintains the same accuracy as the original complex model, yet significantly lowers the average prediction cost, especially in the case of gradient boosted trees. Please read our paper for detailed formulation and results.